Vielen Dank, dass Sie so zahlreich erschienen sind heute Abend zu unserem Meetup und der Martin und dass wir heute eine Rede halten. Und ja, ich möchte mich einfach nur bei den ganzen Sponsoren bedanken, bei Big Data Community Alliance und beim Hub für die Räumlichkeiten. Viel Spaß!
So my name is Martin from Consistor, and I will talk today about CassandraForSQLDevelopers. So the idea behind this talk is to give you some overview about Cassandra features, assuming that you have already some knowledge of relational databases or traditional databases. This talk will be divided into two parts. So the first part will be a theoretical part, when I will go through some Cassandra features and I will compare them with traditional databases. In the second part of the talk, we will create a simple entity model and then we'll query it using traditional SQL queries, and we'll do the same in Cassandra so that you can compare how it differentiates. Okay, let's go through the theory part. So on the left-hand side here, you will see some traditional database features, and on the right-hand side, you can see some NoSQL database features, which are concentrating on Cassandra. Sorry. So we have those 4 letter codes which are describing both databases, ACID and base. And on the first side, it looks like they have nothing in common, maybe with one exception that they both have 4 letters. So there's also a reason for that, because those databases are completely different. So let's go through this ACID terms very quickly, because you already know it. It's just like a refreshment of the knowledge. Atomic update means if I have transaction and this transaction has updates many different data records, then all these records will appear at once. So we don't have to worry about things like dirty reads or phantom reads. It depends on your consistency level in the transaction. Consistency means once you execute a transaction, it will leave your database in a consistent state, so it's impossible that the transaction can apply on part of the data. Whole will go through or nothing. Isolation, so if you have 2 transactions, they do not interfere with each other, so they are running completely in parallel. We know that this is obvious. And durability, if you put the plug off, put it again, the data will survive. So now if you go on this side, you will see actually completely different terms. And if you look at this closer, you will see something like basically, solved, eventually. So actually on this side, nothing is for sure. So the main idea is that RDBMS databases are based on the pessimistic model. So they are and the NoSQL databases are based on optimistic model. So in that case, in RDBMS case, we are committing resources to ensure that everything will go fine. So once you have a transaction here, you can be 100% sure that it will succeed or not. But on the other hand side, you have to commit resources to it, so you have to give up some features like scalability, performance, partition tolerance, and so on. So Cassandra takes a different approach. It uses this base concept. Basically, available means you have a cluster which consists of many nodes. If some of those nodes are down, then the cluster is still online. So maybe you will partially some functionality is not available. But in general, the cluster still works. So it's impossible, or it's quite hard to have a complete crash compared to other databases. So state. Once you execute insert against a database, you might get an answer like, well, it went wrong, but I'm not sure what went wrong, so try later. So actually, probably it will propagate, but the database can give you like an answer, I'm not sure what happened, which is perfectly fine. So you have to just live with that. So we will talk about it later on when we come to transactions. Eventually consistent means if I have kind of transaction, which is called atomic batch, but if I have a transaction which updates multiple records, so it is really possible that some of them will get propagated and the others will get lost, so they will never propagate. So we will end up in a transaction which is partially committed. We will compare those two more details later on, actually, right now. So RDBMS databases, I didn't mention, if you have questions also, then just ask this right online. You don't have to wait for something. Or if you can't understand it, then let me know, or yeah, whatever. RDBMS, we have full transaction support, which is obvious. In Cassandra side, well, there is no such word as transactions. Okay, the latest Cassandra version has something like lightweight transactions, which are basically conditional updates, but they call it lightweight transactions. But I'm going to concentrate on atomic batches. So this is something in a Cassandra world which will get you as close as possible to transactions. But it's not exactly the same. So first of all, Cassandra does not have something like sequences or locking, which means if you have data on your client, which might be a Java client, Python, it doesn't matter. If you send this data to database, it will be written as it is in the database. So database won't modify this data. There will be no veto, no locking, no nothing. This is lock-free database. It's a distributed system. So yes. And this is actually quite a big advantage. We will talk about it later. Why it is a big advantage. From this ACID term, at least Cassandra supports A, I, and D, so without C, when it comes to inserts within a single row. So Cassandra is a database which has tables, columns, and rows, something that you already know. And when you update within a single row multiple columns, then this update will be atomic, isolated, and durable. But this doesn't apply to update across rows. So when you have a batch update which updates multiple rows, then the updates between rows are not isolated, they are not atomic, and they might be not consistent. Within the row, it's given. Eventual consistency. So I would like to explain quickly how the atomic batch is working. So let's imagine that you are going to insert 10 records into Cassandra, right? Within the one single batch. There's a high probability that those 10 records will be stored on a different hosts because it's a distributed database. So what Cassandra does, once you execute this batch, it will create a commit log on the coordinator node. This is the first node that you talk to. And then it will distribute this commit log over a few different nodes. And from now on, this batch was successful. So the data did not propagate, didn't propagate yet, but the insert operation was already successful because Cassandra was able to create a commit log. That's actually sufficient. Now this commit log will be stored on a different host, and each of these hosts will try to write the data where it belongs. And it's, let's say that in our case, we have to store this data on 5 different nodes. And 2 of those 5 nodes are offline. So we have an atomic batch, which tries to insert data on 5 nodes, but 2 are offline. So at the beginning, the update will propagate on those 3 nodes, and the remaining 2 nodes won't get this update, because they are offline, it's obvious. Now what can happen is that those coordinator nodes will die and never go back online. So these remaining 2 nodes will never receive their updates. This is very unlikely to happen because a lot of things would need to go wrong, but it could potentially happen. And one more thing, in that case, so when the 2 nodes were offline, you would receive actually an exception from the client, also from the Cassandra server, which will tell you something like, well, I couldn't propagate it completely, but I don't know what happened. Okay, that's it. Now, this sounds in the beginning actually quite strange. You would like to say, okay, I would like to have this full transaction support. I don't want to have this one on the right-hand side because it's actually quite fuzzy and so on. But the fact is, Cassandra trades this full transaction support for something else. It trades it for partition tolerance, availability, scalability. You can, and this is what you are winning. And you as a developer, you have to learn to live with this fact. So For example, what you have to do, never read your own writes, which means if you are executing some insert into the database, you have to be optimistic. You have to think, okay, it will propagate. And you have this data on the client, which you have inserted into the database, because the database won't modify this data. So you can keep working with this data that you have on the client. So actually you don't have to wait for the response from database, just send it, and even if you get an exception, keep working. Just give the message to the customer, wait a few seconds, the data will show up. I mean, everyone probably has seen such message, so must be reason for that. So once you understand it, and you can also minimize the chance that something will go wrong by right cluster configurations. I mean, if you are replicating data on the same hard drive on a different partition, then no one can help you. So you have to be smart enough, actually, and then you can really get close to those transactions and still maintain a cluster which scales. Okay, the next thing is inner joins. The traditional databases have good support for inner joins, but this had of course some drawback, because if you are going to support efficient inner joins, then also that means that the tables are tightly coupled with each other, so you can't put them on the different servers or something like that. So having inner joins limits horizontal scalability. You can't split your database on different machines. Cassandra does not allow inner joins. It actually even does not have really indexes. It has something like, I mean, it has indexes, but we'll talk about it later on. So basically, they are forcing you to create one table that will answer only some limited subset of the queries. So you have to denormalize your data. Okay, this fixed summary is not really important. Cup triangle. How many guys know this cup triangle? How many of you guys heard about it? Okay, then we'll skip it and we'll talk about it later because we can get to more interesting things. Data modeling. Data modeling. Okay, so we know how we do it in a traditional database. So first you start with a domain model, which is high-level UML-like model describing relations in your company, right? Made probably by people who does not have really technical understanding, which is actually very good to have something like that as input. This is the first thing. Actually, in both databases you would start with that. In the second part, in the traditional database, so here, you would create normalized entity model. You would apply all normal forms to this entity model so that there are no repeating values inside the columns, that every table has a foreign key, and so on and so on. And in this phase, you are actually not thinking about performance, about how you are going to query this data. Only what matters is actually to have a nice entity model. Because, you know, doesn't matter how it looks like, you can only query it in any possible way. You have to just create right indexes and you are fine. And this is the part when it gets really different in Cassandra. And I'm definitely sure that some of you will have problems with that, but you have to live with it. Because remember, you are winning horizontal scalability, partition tolerance, availability, but then you have to live with other modeling techniques. We are starting with domain model, okay, this is obvious. But then the second point is already different. I told you already that there are no inner joins between tables, and there are also limited possibilities how you can query a particular table. There are a few cases how you can query the table. This forces you to know your queries up front, because based on the queries you are going to create your Cassandra model, which means if you don't know the queries, you can't start developing. And maybe if you're already done with development and they are showing up new queries, then there is high possibility that you will have to create new tables and you have to migrate the data into these new tables. You have to fill them up. So this is actually very important to to know your queries before you start development. And also, which is actually quite a good pattern, you shouldn't create you shouldn't create one table to answer single query. So the relation between amount of queries, amount of tables shouldn't be one-to-one. What you could do is like collect all your queries, create a ranking, and create tables only for the most frequent queries. And those less frequent queries, maybe you can answer those with few other queries, maybe partial tables can, or maybe you can use Hadoop on something else. I mean, from Cassandra perspective, it really doesn't matter if your inserts 10 records or 50 records, it's very fast, so it doesn't matter, but you have to remember that you have to maintain this data. So if you replicate your data on many different tables, then you will have many different replicas of the same set, and you have to maintain. So you need those tables, but try to limit the amount. Okay, so in Cassandra first we have domain model, then we are defining our queries. Based on those queries, we are defining our tables, and the model is denormalized. That means, well, it's not like here where you have normal fonts. Nobody really cares whether your database looks nice or whatever, it has to be performant. So do whatever you like to. If it's fast, then it's fine. No one is going to argue with that. So those times are over when we spend hours thinking about some theoretically nice designs. I mean, the only thing that here matters is actually performance and quality of the data. So there are actually no real patterns or solutions for every problem. So maybe you can just look at the internet or something. That will be all for the theoretical part. Any questions? Now we'll go through some real examples. No questions, but you can follow me and no one is sleeping. Or okay, I'll take it as yes. I mean, that no one is sleeping.
I almost fell asleep.
Yeah,
I almost fell asleep.
Me too, but it's a different story. Okay, surprise, surprise. We will model a tweet database. Twitter, actually. Quite simple. But everyone knows Twitter, so I decided to choose something which is similar to Twitter because at least I don't have to describe the use case. This is the entity model, right? Well, I don't know the language here, but it's definitely, well. So the users table is normalized, we have primary key, we have names here, and the email address. There is index on this email address. We are starting from a SQL part because we don't know the queries yet, so I can't go to Cassandra. So that's why I started with traditional database. So you can query users by email, and then you will get a primary key. This primary key leads to tweets table, as you can see here. So this is a join between this primary key and this foreign key here. They are also blue. So we can see that the Frido user, you can read it. Okay, that's good. Okay, so you can see that the Frido user has 3 tweets, one after another in 5-minute intervals with some text and with some icon. Yeah? The Wilbur user has 2 tweets. Okay, that's fine. And the Olmo has no tweets. But the Olmo is following. Who is following? Okay, the Olmo, that's his foreign key, and he's following the both users. So he's following the Frido and the Wilbur. Quite simple. This is clear, right? Okay. Good. First question, display the latest tweet by Frido. So this is our whole model, and displaying the latest tweets of user Frido will lead to such response. So basically we have inner join users on tweets on this key here, right? And we are selecting from users where email address is blah blah. That's the select statement. I'm not going to execute it, I think that you believe me. So select tweets, inner join tweets on users on primary key, foreign key, where email Frido, order by, take test ending, because we would like to see the latest tweets at the beginning. It's a logical thing. Once you log in into Twitter, you see what happened the last time. What is the next? Okay, the Cassandra part, good. This is the create table statement in Cassandra, which is very similar to SQL. They changed the query language in Cassandra 1.2. Which one was it? 1.2. Yeah. So now it's SQL-like. Some people does not call it no SQL, but not yet SQL. So there are some similarities. I wanted to warn you also in the beginning about one thing. So you have these traditional databases like RDBMS databases. You're used to terms like transactions, isolation levels, atomic, and so on, right? Now if you move to those NoSQL databases, then basically every database is different. And they're using the same terms, but they might have a different meaning. And just really make sure that once you are reading documentation, you are reading to the bottom of the page. So don't leave it like, okay, it's atomic, and that's fine, I understand what it means. There's nothing wrong with that. The people have to need some names for the new terms, but each database is different. That's the reason why they are reusing the terms, but they might have slightly different meaning. For example, those atomic patches that I talked to, they are atomic, but actually only within a single row. So when you update multiple records in a database, then across rows the update is not atomic, but within a row. This is perfectly fine. You have to just read the whole documentation. So the atomic patch is atomic within the row, but not across the rows. On the other hand side, it's obvious that you would update multiple rows within a patch. You just have to know it, because otherwise you might get disappointed. The same about, doesn't matter. Just read the whole documentation and make sure that you understand what it's meant, then you are fine. Okay, then we will create a table tweets by date, because we already know our query, which was select the latest tweets for any user. So this is the table tweets by date. It has email, icon, tweet date, and text, which is basically everything that we need for a tweet. You won't see your primary key because there is no such thing like primary key in Cassandra. So this is log-free database. You can't generate the primary keys. There is no locking, which means you have to make sure somehow the email is unique. I mean, you can use the conditional updates in the new version of Cassandra, or you could use cages or something, or some other database to make sure that there are no duplicated users. So no primary key. I mean, there is a primary key, but not like a sequence. And of course, we have a primary key in the meaning of Cassandra. And this primary key consists of two parts. The first part is an email address, which means, okay, we are going to find tweets for the particular user given by an email address. And the second part is a tweet date. If you want to sort the data by some criteria, it has to be part of the primary key. And I would like to have those tweets sorted cascading by tweet date, which you can see here. So that's why this is the second part, primary key. We will talk about it later because there is much more behind it. But for now, actually, I'm quite sure we can straightforward answer our query. So we have a primary key, we can query it by email and tweet date. I will try to give you some practical examples so we can just query online. And you can see how it's working. This is a small tool that I have for the session that I have implemented for Cassandra where you can execute queries. I will use it because I need something to execute queries. So I have created our Twitter database, if you have seen on the slide, so you can see here something like use SQL demo. It's basically something like a database instance that I'm connecting to. Okay, dropping table, create table, that's something what you have seen already. And then we have inserts. Those inserts look exactly like the insert that you know from SQL. Exactly. Right, so good, then we can start querying our data. I don't know why it's in the part of it. Doesn't matter. This is the right part. First I have to switch the database instance and then tweets by date. But first of all, we can select all tweets. No, wait a second, I will organize it differently. Oh, why I can see only the part of the stuff. This sucks. I don't know why I have to scroll, but okay, doesn't matter. So once we selected all tweets, you can simply see that first they are grouped by the primary key, which also by the first part of the primary key, which was the email address, and then they are automatically sorted by the tweet date in the reverse order. This is what I have promised you once I created the table. So now we can select tweets only for particular user. Okay, so when the user would log into Twitter, they would like to see his latest tweets. This is exactly the query that you would have to execute. You would get automatically tweets sorted by this date, by the latest date, with all the data that you need actually. Actually quite simple and straightforward, right? You could also sort it in the reverse order. That would work too. Okay, so as you can see, we can query this data by this first part of the primary key, which is actually pretty good. We will now query it by the second part. What was that tweet for that? Okay, this is working fine. So we have provided two parts of the primary key, which leads us to a unique response. Now, as you can see, we have queried it. This is a history. So we have queried it by email address, and by email address and the tweet date. So both work fine. Let's try to query it by the tweet date then. So by the second part of the primary key. Okay, this doesn't work, and there's good reason for that. I'm going to here put allow filtering. This basically means enable denial of service on my database. So it executes a full table scan across the cluster on each node. So now I would like to try to explain what's the reason for that I can't query by a quick tweet date. So what is the pattern to execute the queries against this table? What is possible and what is not possible? You see, because there is another thing about those NoSQL databases. Okay, that's what if you look at a traditional database, you can, as a developer, you can write your queries as you like to, and if they are slow, then someone will execute, will give you these execution plans, and maybe you will have to change something in your query, but that's all. So until now, you didn't have to worry about performance once you have written the queries. I mean, you can write a stupid thing, that's obvious, but you didn't have to really pay attention to that. Now the things are a little bit different, because now you as developer, you must also understand what happens behind the